What is an LLM? An LLM is a large language model. And what exactly is a large language model? It's a model that has been pre-trained on an enormous amount of data. When we talk about large language models, we're referring to models like GPT 3.5 and GPT 4, which power ChatGPT in both its free and paid versions. There are open source models like Llama, Mistral, and other closed source models like Claude and Anthropic. In essence, there are many models, but the most well-known are those powering ChatGPT. So what defines an LLM from this new generation? Let's break down GPT from ChatGPT. It stands for Generative Pre-trained Transformer. These are large models of this new generation. The transformer architecture emerged around 2017 in Google's research papers, though Google didn't implement it at scale initially. Instead, a startup called OpenAI, which everyone knows now but was only known to insiders then, adopted this technique. Other research papers suggested that scaling up this technology would lead to powerful LLMs. Why do we talk about tokens in LLMs? Because LLMs don't actually understand text. They only understand numbers, as they operate on matrices of numbers. We need to convert text into numbers, and one way to do this is through vocabulary. We take words, parts of words, or symbols and convert them into tokens, the famous tokens everyone talks about. Since these tokens come from a finite vocabulary, for example, Llama 2 has a vocabulary of 32,000 different tokens. We can assign a number to each one. This allows us to convert our texts into numbers and represent them in matrix form. These LLMs are organized in layers. The first layer, from left to right, translates text into numbers. The subsequent layers, called hidden layers, capture patterns and meanings from the input. Finally, at the output on the right, the model predicts the next token. For example, if we pass the quick brown through the LLM, it predicts the next token. We see several possible predictions on the right with values corresponding to the statistical likelihood of each potential next token. In the simplest case, we select the most probable token. Looking at our example, the word fox has the highest probability among all possible output words, so it's selected. This is exactly how statistical models like GPT language models work. You might say, well, one word isn't enough. Indeed, to generate an entire sentence, we simply predict the next word, take the sentence plus the predicted word, pass it back through the model to predict the next word, and so on. And this is why these models are typically quite slow, and we measure their speed in tokens per second. Each token requires a complete pass through the entire model. It's actually more granular than words. We're processing at the token level, which can be parts of words. When we want to utilize these models with our personal data, we encounter an important limitation. The model has no knowledge of data that isn't part of its training set, data that isn't available on the internet. When we ask questions about such private data, the model simply cannot provide accurate responses. This is where the RAG approach, retrieval augmented generation, comes in. While I won't go into great detail or demonstrate it now, it's a technique that's particularly valuable for businesses. Here's how RAG works. We pair our LLM with what's called a vector database. Think of it as a private knowledge repository. Before querying the model, we search this database for relevant information. We then take this relevant context and inject it into the prompt, asking the LLM to respond based solely on the provided information. This is one of today's most popular techniques for expanding a model's knowledge without retraining. The third method is fine-tuning, which serves two main purposes. It can enhance the model's knowledge through additional training on specific datasets, or it can teach the model new techniques rather than new knowledge. In our case, you'll see how we use it to teach the model to output JSON in a very specific format. Fine-tuning is about teaching new skills rather than just adding information. For instance, chatbots are essentially fine-tuned LLMs. By default, an LLM, as I mentioned earlier, simply predicts the next word. But a chatbot needs to do more. It needs to maintain a conversation, understand context from previous exchanges, and respond appropriately to follow-up questions. This interaction capability is a skill that requires fine-tuning to achieve. Think about GPT 3.5 compared to GPT 3. The chatbot capabilities were achieved through fine-tuning the base model to handle conversational interactions. Prompting and fine-tuning can often achieve similar results. The general approach is to start with prompting, as it's more cost-effective and less complex than fine-tuning. If prompting proves insufficient, or if we run into context limitations, remember, models have limits on prompt size, then we might consider fine-tuning. What are the key benefits of fine-tuning? First, it provides more stable outputs. This is crucial when integrating an LLM into function calls where our programs need precise, syntactically correct text rather than approximate responses. It can also lead to token savings, as teaching the model new patterns can make it more efficient. However, fine-tuning requires GPUs in most cases, and you need training datasets. These datasets either come from existing sources, or you need to create them yourself, which isn't a trivial task. Let me walk you through the process. For our experiment, we'll use a Mistral model, specifically an instruct version of Mistral, which is a pre-trained base model. We'll teach it a new trick, a new task. This is what we call transfer learning. To summarize, we take the pre-trained model, which has already learned from a massive amount of data, and fine-tune it on a small specific dataset. The result is our fine-tuned model. While fine-tuning requires less data and computational power than pre-training, these models still have billions of parameters. Mistral 7B, for example, has 7 billion parameters. Using 16-bit floating point precision FP16, just loading the model into memory requires 14 gigabytes of RAM. The training process demands even more memory, which means we need reasonable hardware specifications to fine-tune a model. This is where optimization techniques become crucial. Enter PEFT, parameter efficient fine-tuning, and specifically a method called LORA, low rank adaptation. Without diving too deep into the mathematics, LoRa allows us to train only a small portion of our model by creating adapters. Picture it like this. We have our model with its pre-trained weights, and we create a LoRa matrix divided into two parts. We train only certain parameters to create an adapter, and the combination of the original model and this adapter creates a new model with the desired behavior. As mentioned earlier, fine-tuning requires new data. We can create this data manually or use other models to generate what we call a synthetic dataset. For instance, we might use ChatGPT or GPT 3.5 to generate our training data. Quality control is crucial here. Poor quality training data can severely degrade the model's capabilities. For our demonstration, I'll be using H2O LLM Studio, an open source graphical tool from H2O. I particularly like this tool for several reasons. It doesn't require coding knowledge, it provides clear visual indicators of performance and training metrics, and it includes testing capabilities. The tool even includes a chatbot interface for testing our model, though it has some limitations. Before we begin fine-tuning, we need to select a base model. I recommend using Mistral 7B Instruct, an open source model that's quite capable and well suited for our use case. What we want to achieve is the ability to ask the model questions and have it respond with specifically formatted JSON output. I'll show you an example where we present questions about comets to Extia, provide 4 options, and expect the model to generate JSON following our prescribed format. Let's start by clearing the terminal. We'll run this code that loads the model, uses a tokenizer to process our prompt, generates a response, and displays it. Looking at our results, we can see the model has improved. It can generate JSON. Our question is correctly placed in the question field. The 4 options are properly formatted as A, B, C, D, and the answer is marked as D. It understood our requirements well. However, there's an issue. It adds JSON tags around the output. This happens because the model is configured for chatbot-style display. While this formatting might look nice in a chat interface, it causes problems when we want to use the output in function calls. Moreover, though I haven't shown you, the output can be inconsistent. Sometimes the model understands our instructions perfectly but decides to add its own formatting or explanatory text like, "Here's what I managed to do based on your data." What we want is stability in the output, pure JSON with no extra characters or formatting. While our model is performing well, it's not quite giving us the exact behavior we need. Our fine-tuning goal is to achieve consistent, clean JSON output. Let's take our Mistral 7B Instruct model and create a dataset for this purpose. Let me show you how I created the dataset. Here we have questions and expected outputs. I'll demonstrate with an example. The question or questions are my quizzes, with instructions and expected responses carefully formatted. I've written a small program that processes these files. Some were created manually, while others were generated using GPT 3.5 or GPT-4 to produce exactly the format we need. We're creating a training dataset with matched question-answer pairs. The data is stored in the Parquet format, which is popular in AI and big data applications. It's similar to CSV but more advanced, allowing us to store both our instructions and expected outputs efficiently. Our training dataset consists of about 10 records. That's quite small, but it's sufficient because our model is already close to producing the output format we want. Now let's get to the serious part. Training our model using H2O LLM Studio. While there are many tools available, I prefer this one for its focused approach to fine-tuning. First, we'll import our Parquet files. We'll create metadata called train data and map our instruction columns and response instructions. The prompt column contains what we'll give to the model, the question and any additional instructions. The answer column contains our expected JSON output. With our dataset prepared, we'll create an experiment. We can either start fresh or build upon a previous experiment by modifying parameters. We can even save our configuration in a YAML file for future use. There are numerous parameters to consider. For the training dataset, we're using causal language modeling for question answering. We're fine-tuning the Mistral instruct model. Regarding dataset settings, we need to consider the maximum length of our prompts. We analyze our data to find the longest input and ensure our parameters can handle it. This is important because during training, we pad our text to maintain consistent lengths. The GPU processes matrices more efficiently when they're uniform in size. Our models typically use 32-bit or 64-bit floating point numbers, meaning each parameter takes 4 bytes by default. They're often saved in 16-bit floating point format. Using 2 bytes per weight, we'll quantize our model to 8-bit integers, reducing memory requirements while maintaining acceptable performance. The number of epochs is crucial, especially with our small dataset of just 11 training examples. To prevent overfitting, we'll limit the number of epochs. If we had more data, say around 100 examples, we might use 10 epochs. The goal is to avoid having the model perform well only on seen data while struggling with new inputs. We want stable JSON output regardless of the input question, as long as it follows our format. To achieve this without overfitting, we'll keep the epoch count low. Batch size affects optimization. We can process multiple questions simultaneously, though this requires more memory. I'll leave the advanced parameters at their defaults for now. The LoRa parameters and quantization settings allow us to train models on consumer-grade GPUs rather than requiring data center hardware. We won't modify the LoRa target module for this demonstration. For validation scoring, we measure how well the model performs on unseen data after each epoch. I prefer using GPT 3.5 Turbo for scoring, as it provides detailed feedback and a score out of 100. Let's start the training process. Our experiment is queued. Now it's running. We can monitor the progress here. It's loading the model and beginning training. We're on the first epoch, processing the entire training set. That's complete, and now it's moving to validation. This takes longer because it needs to call the OpenAI API. Interestingly, it's using BLEU scores rather than GPT scores for this first epoch. Might be a bug in the current version. The learning rate shows how quickly the model adapts. We start with a low rate and gradually increase it. We're also tracking the loss, the gap between predictions, and expected results. Our graph won't show perfect convergence given our limited data and epochs, but typically you'd want to see the loss decreasing over time. Now let's use a previously trained version that was fine-tuned using the technique we discussed. We'll use the same code to load the model and ask the same question to compare the results. Notice the difference. The previous version included JSON formatting tags, but our fine-tuned model produces clean JSON without any extra characters. While this might seem like a small improvement, it's crucial for stability when integrating the model into production systems. If we're using this output in a serverless function deployed on GCP to generate Google Forms, for example, any instability or extra text would require extensive code to clean up. Fine-tuning for our specific use case ensures stable, predictable output that we can use directly in our application workflow. This demonstrates a practical use case for fine-tuning, taking a capable base model and refining it to produce exactly the output format we need for our application.